demonetized anyway.
Demonetized.
That's okay.
The 1 million subscribers.
Alright, so what did we talk about yesterday?
Improper
Improper integrals, right? And how can we recognize that we have an improper integral pretty quickly? Or the first type of improper integral? We didn't talk about that? I think we did.
We haven't, I didn't really get it situated.
What could help us identify or help us know that we have an improper integral right away?
The formula.
If it's 1 over.
Very good. When one of the bounds on the integral is what?
Infinity.
An infinity, right? We wrote it right here. Infinity or negative infinity as a what? Bound. That's a quick way of identifying that we have a improper integral. Really fast. Those are easy to identify. So that's the first type, which is where one of the bounds is infinity. Okay, that's the two cases, the top or the bottom. And the third case is where both of them would be infinities. Okay, from negative infinity to positive infinity. So there's 3 cases for the first type, which is where the bounds have an infinity in it. Pretty easy?
Simplistic.
Today we'll probably get to talk about the 2 cases where the top is infinity or the bottom is negative infinity. And then we won't be able to talk about the other one until probably next week. Okay? Sounds good?
Great.
Yeah. And then we'll also learn how to recognize problems written in a certain form that follow a particular pattern. And there's a certain rule that goes with them. And the reason I'm going to expose you to those is because we're going to use them later when we start talking about series. So it's going to be important to kind of already have an idea of what they are and recognize. It'll come back to you when we get to series eventually. You'll be like, oh, I remember we did that when we did improper integrals. It'll come back to you.
Forgot about series.
Cool? Alright, so we did 2 examples yesterday through exploration, and we looked at this one, 1 over x. And what did we say was happening as we accumulated that area as we went further and further to the right?
They got bigger and bigger.
So that area that we were accumulating continued to grow, right? And it continued to grow what?
Bigger.
It continued to get bigger and bigger, so it went towards what?
Infinity.
Infinity, right? So we kind of went through this example and we said, well, that's what should happen every single time we have a graph that does this, right? If the graph continues forever to the right but never touches the x-axis, well then there was always going to be an amount of space between the curve and the x-axis that we could add to the previous area, right? So it should continuously grow.
Yeah.
But then we did another example, right? That did the same thing, yet its area was what?
Finite number.
Finite number, right? And what do we say was the main difference between these two?
So it's going at a faster rate. It's that one.
So one was getting closer to the x-axis, what?
At a faster rate.
At a faster rate, right? And that was the main difference between them. Okay, so the defining factor, whether it ends up going towards infinity or ends up going towards a finite number, was the fact that it got closer to the x-axis faster. Does that make sense?
Yes.
Yes? So because it was getting closer to the x-axis faster, we were getting to a point where it was what?
Super small.
Where it was closer to the x-axis, right? Sooner? So that space between them was what?
Close to 0.
Super small, right? So close to 0 that it was like if we were practically adding what?
0.
Adding 0, right? We're adding nothing to the previous area that had already been accumulated. Does that make sense? We can accumulate so much area up until a certain point where we start adding what?
Nothing.
Nothing, so therefore it doesn't seem to grow, right? But in theory it should continue to grow, right? But we're just adding such a small amount that it's like we're adding it. Cool?
Yeah.
Yes?
Of course.
Alright, awesome. So there's 2 new words that we're going to introduce today. One of them is the word converges, and the other one is diverges. Okay? So for example here where we got a finite number, we could say that that integral is converging towards what?
The x-axis. 0.368.
0.368, right? So you're going to see in a little bit that what we're finding is actually a limit. Okay, and the limit is 0.368. Okay, so that's why we say that it's converging towards that value. The limit is about what happens as we approach something, right? We're approaching this particular value. Will we ever actually get there?
No.
Maybe, maybe not, right? But we're approaching it. That's what limits are all about. Okay, what's happening here?
It's going to infinity.
Going to infinity, so this would be an example of something that we would say
Die.
diverges, right? Okay, so converges means that the limit exists and is equal to a finite number. Diverges means the limit does not exist, right? So it would approach some infinity. Cool?
Excellent.
We're good with the words?
Yeah.
When we get to sequences and series, we're going to use the word converges and the word diverges all day, every day. So that's basically what they mean. Not too bad?
Great.
Maybe sort of, kind of?
That's very nice.
All right, so ready to discover how to handle these particular types of problems? Yes?
Yes.
How to actually work them out mathematically? Woo! Let's do it. So today is the 30th, and we're continuing the notes from the previous day. And we're going to talk about how to deal, okay, with improper integrals. Now remember, this is the first type. Type 1. So these are the easy ones to identify because they're going to have some infinity as one of the limits or both of the limits. Okay? And we're only going to talk about the two cases today, which is case 1, which is where the upper limit is infinity, and case 2, which is where the lower limit is negative infinity. Seems easy?
Yes.
Alright, so technical stuff. If f is continuous on the closed interval from a to infinity, it has to be continuous in that interval that we're working with, then we can say that the improper integral from a to infinity, which is the forms we were exploring yesterday, of that function f of x dx is equal to, okay, the limit as b goes to infinity of the integral from a to what?
Infinity.
A to b of f of x dx. So this is kind of my way of fixing the problem of having an infinite bound up there. I don't have an infinite bound now in theory, right? I have some letter b that represents some number, right? And what do I want to do?
Value. No, find the limit.
I want to what to infinity?
Substitute it. What?
I want to approach infinity, right? I want to know what happens as I get really close to infinity. Does that make sense? Yes? Right. That would be like going to infinity. So to work this mathematical problem out, you have to do how many things?
Two.
Two things, right? Really it's three, but we can do two. So what would be the first thing to do? Actually integrate the function, right? See what we get. And then
Substitute.
substitute or evaluate, right? Evaluate from A to B. And then my result, I want to do the what to that?
Find the limit.
Find the limit of that as b goes to infinity. So it's really like three things, okay? Integrate, evaluate it from a to b, and then the third thing is to actually find the limit. Throughout that entire process, I need to continue to write the limit notation. Okay? I can stop writing the limit notation once I'm ready to actually what?
Find the limit.
Find the limit. If you don't do that, you're going to get it wrong on the free response on the AP test. Okay, there will be improper integrals, and they will ask you to solve the improper integrals through the limiting process. So you need to show this notation. Okay? On the multiple choice, you can get away with not showing it if you wanted to. Okay, and I'll kind of show you how to handle those maybe when we come back next week. Kind of how to do these problems without showing the limiting notation for multiple choice problems. I don't want to show it to you today because I don't want you to do it today, because I want you to actually do it the long way and actually show that notation so you don't forget it on the free response and then lose those points there. Because they're easy points to get, right? It's easy to write the limit.
Yeah, but
Yeah?
tedious.
You don't want to lose the point for not writing the limit like on the quiz we took, right? Cool? Okay. So, case 2 is very similar to that one, right? Except on this one, it's if f is continuous on the open interval negative infinity to b, then the integral from negative infinity to b of that function, improper integral, because it's got an infinity there, how would I write it?
Yeah, the limit.
The
as
limit,
in the
a, okay, I like that,
goes to b.
a goes to b,
No, the
no?
negative
It
infinity.
goes to negative.
A goes to negative infinity of
Integral
the integral,
of
A to B.
negative
A to
b of
Of?
f of x dx.
beautiful, of f of x dx. That's how I would handle that, yeah. Could I use any letter? Did I have to use a?
No.
No, I could have used g approaches negative infinity and put g to b, right? I just kind of used a because, well, a, b, makes sense. Yeah. Cool?
Yeah.
Got it? Ready to do some examples and see if we can work them out by doing all this that we have to do? Let's do some, okay? It's pretty easy. Here we go. So 1a, I'm gonna try to do 3 examples and I'm gonna do them side by side, so kind of leave space, okay? Don't write so large. And I'm doing it like that because they're gonna be kind of related and we're gonna try to see if there's a particular pattern that's happening. Ready? Alright, so let's do the integral from 1 to infinity of 1 over x to the 3 over 2 dx. Was this one similar to the one of the ones we did yesterday?
Yes.
Which one? What was the one we did yesterday?
1 over
1 over x to the first, right? This was 1 over x to the what?
3 over 2.
3 over 2, which is 1.5. So this one's what, a little bit larger power, right? So what do you think this one's going to do? Do you think this one's going to diverge or converge?
Convert.
Think it's going to converge?
Yeah.
So do you think he's going to get closer to 0 faster?
Yeah, convert.
Why?
Because he has a higher power.
It has a higher power, so when I raise something to a higher power, then I have a
No, you have a faster rate.
a larger number, right? And if I have a larger number faster in the denominator, that means this fraction is going to get smaller and smaller faster, right? So it's going to get closer and closer to 0 faster. Does that make sense?
Yeah.
Yes? So do you think this one is it going to be fast enough though? That's the question.
No.
How much is fast enough? Right?
We don't know yet.
Well, let's see. Let's do the math and see what we end up with, okay?
Yeah.
Cool? How would we know it converges? What should we end up with at the end?
A finite number.
A finite number, right? If we get an infinity, then it
Diverge.
diverges. Okay, so what's the formula to work this guy up?
The
The
limit
limit
as one. No. B goes to
as
infinity
b goes to infinity,
equals
no,
of
of the integral
the integral of 1
from 1 to b.
b.
Can we rewrite this guy to integrate him easily?
Yeah. Yes.
X to the negative 3 over 2 d. Alright. So far so good. Let's actually integrate him because that's what we said we had to do first. So add 1 to the power, x to the negative 1 over 2, and then we're going to multiply by his reciprocal, which is
Negative 2.
negative 2. We have to evaluate him from 1 to what? B, and then we have to get the what of all that?
The limit.
The limit as b goes to infinity. So far so good? To make your life easier, get that negative 2 out of there. Do this, the limit as v goes to infinity of negative 2 times, and then let's actually evaluate. So pretend the negative 2 isn't there, so it becomes easier to do. Yeah? Plug in b, what do we get?
B to the negative 1/2.
b to the negative 1/2, which is the same thing as?
The square root of b.
No.
Oh, no, no, no.
1 over the square root of b, right?
Yeah.
We agree? Minus, that's how we evaluate, right? Plug in the bottom limit. What do we get for that one? 1 over square root of 1, which is 1. Yes? Alright, cool. So now we're ready to actually evaluate the limit, right? So in our minds, we're gonna plug in infinity, but we're not gonna actually write that down. Okay, so really, when you're working this out, what is your concern? Where do you kind of have to imagine that you're working? This is only as b goes to infinity, so you're only really looking at the parts that have what? That have the b, right? Okay, so what's going to happen if I were to get the square root of a very large number? Let's say infinity.
It's the infinity.
The square root of infinity is infinity?
Yeah.
Oh yeah, duh, right? Infinity times infinity is infinity. It's a perfect square, right? Awesome. So infinity. So 1 over infinity is basically 0, right? So here we can stop writing it, the limit, because we're taking it already. Negative 2 times 0 minus, what does this give us? 1. So what do we end up with?
2.
2?
Number 7.
Perfect. Wow, so was it enough?
Yeah.
Was that 0.5 enough to make it grow fast enough for us to end up with a finite limit?
Yes.
Yes? So what can we say that this guy is doing, this integral is doing?
Converging.
He's converging, right? So he converges, and we're going to say towards what?
The x-axis.
No?
Towards 2.
2.
Towards 2, right? Will he ever actually get to 2? Maybe, maybe not, right? We don't know, but we're going to say he converges towards 2 because he's getting really close to 2. Or maybe he's a little bit